The quest to find planets outside our own solar system. You're listening to Are We There Yet?, the radio show exploring space exploration. Hi, I'm Brendan Byrne. For decades, scientists hypothesized that planets existed around other stars, but it wasn't until the 90s that they confirmed them. Now the field is booming, and scientists are pretty sure every star has a planet orbiting it. They're called exoplanets. The Kepler Space Telescope was launched in 2009 to look for more of these exoplanets, but as Jason Steffen claims, the telescope changed our understanding of the universe. We'll speak with Steffen about his new book, Hidden in the Heavens: How the Kepler mission's quest for new planets changed how we view our own. Then, aside from Kepler, how else do we find other planets? And could we find evidence of life within their atmospheres? We'll speak with Florida Tech's Eric Perlman about what makes these planets unique and how they were discovered in the first place. That's ahead on Are We There Yet? How many planets exist outside our own solar system? That was a fundamental question scientists wanted to answer when the Kepler Space Telescope was launched in 2009.
4, 3, 2, engine start, 1, 0, and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Since then, the telescope found over 2,700 planets orbiting different stars before its retirement in 2018. For Jason Steffen, who worked on the Kepler mission, the telescope's discovery changed the way he viewed the universe. Steffen is an associate professor of physics at the University of Nevada, Las Vegas, and the author of Hidden in the Heavens: How the Kepler mission's quest for new planets changed how we view our own. Steffen spoke with our Are We There Yet intern, Jenna Weiss, about his book and his career with Kepler. Here's their conversation now.
Jason, welcome to the show. So this book is an insider account of not only the Kepler mission, about your personal mission too. How did it feel to go from a grad student working on a practice problem to publishing a book on this topic?
It was kind of a long time coming. I didn't anticipate writing a book about it, but I did feel like I had, the inclination as the time progressed. I will say that beginning as a graduate student, it was kind of surreal because I view myself more as a physicist than an astronomer. And so initially thinking about working in cosmology and black holes, that was a lot more physics-oriented than studying exoplanets was. But the practice problem really turned out to be interesting and timely. And so going from being a graduate student, working on something that was kind of the backup plan, kind of realizing that it was a lot more interesting than we anticipated, and then having it morph into the dissertation. And then I guess the most surprising thing of all was the fact that right after we finished was the time when that expertise was needed by NASA to help kind of advance the Kepler mission.
So I do want to talk about when you were selected by NASA to join their science team. Just how little did we know about exoplanets at that point, and what kind of questions did the team aim to answer when designing the Kepler mission?
It's interesting because the design of the Kepler mission, it happened at a time when we didn't know anything about exoplanets. The beginnings of the mission concept happened in the 1980s, and so that was before any exoplanets had ever been discovered. We only had the solar system to use as a model for what we would expect planetary systems to look like. And so the anticipation was that it would be planets like the Earth, planets like Jupiter on one-year orbits or decade-long orbits. So the chances of finding something were really small. We might only find a few dozen planets altogether. By the time the 90s rolled around and Kepler was in the proposal process, when they'd already submitted some proposals and had been working on revisions, throughout the 90s, exoplanets started to be discovered, and they were way different than anyone had ever expected them to be. So, the first planets discovered around a sun-like star had orbits of 3 days instead of 30 years. It really kind of broke our planet formation theories. And so we had to reconceive, what is it that we're going to learn from a mission like this? Kepler was selected right on the heels of the first transiting exoplanet discovery. I don't think that specific discovery drove Kepler to be selected. I think it already had a good chance of being selected anyways. It came to be a time when we really didn't have any idea what we were going to find. We had no idea the extent to which Kepler would be successful at finding exoplanets.
Right after that, I believe it was the first mission of Kepler. You talk about it in Chapter 3, where there is a semi-casual meeting with scientists at a random Florida restaurant, and it's where you say it formed one of the greatest scientific collaborations of NASA's history. We'd love a seat at the table. Can you kind of walk us through what was discussed and how that impacted the trajectory of Kepler and the culture of the team?
By this time, so I joined the science team as a participating scientist, which is pretty common in NASA missions for them right at the time that the mission's about ready to launch, they'll bring in new scientists in order to fill out the science team. You don't need someone to bolt the instrument together anymore. Now you need people to take the data and to the scientific inferences that the data provide. And so I was brought on with the participating scientists. We'd been meeting together for about a year at that point. And so when the launch happened, we met together, a group of people who had been recently brought on, along with Jack Lissauer, had been on the mission for quite a while. He joined in the 90s. But we sat together at this restaurant. I remember dragging the tables across the floor so that we could all talk to each other. And we just sat down and started talking about what our interests were, what we were hoping to get from the data, what kinds of studies we wanted to lead, and then how that collaboration would work, how we would talk to each other, how we would decide who got to do what project, how we would decide who helped with who doing what project. One of the things that working group did collectively, it really changed the culture on the mission, because as we started working together and the way that we collaborated with each other, it served as a model for the other working groups on the mission. So there were people who were measuring the number of Earth-like planets in different orbits, like a small planets working group. They had working groups that was doing follow-up observations. They had working groups that were looking at noise mitigation. And so all of these different groups around the mission used the way that we functioned.
Definitely. So by the time you guys had your meetings, it came down to selecting the final target list of the stars you're going to look at, specifically the top 3%. Kepler had to be very picky with the mission requirements. What were some of the obstacles and the most exciting discoveries when it came to observing this final target list?
The target list was selected from the Kepler input catalog, which is several million stars that had been observed from the ground. Most of it took place before I got there. After I got there for about 6 months, there were still refinements done to the catalog of ultimate targets. The Kepler mission only collected data on specific targets. They didn't do full frame images. And so they had to down select from the few million stars that are in the field of view to the 150,000 targets that were going to be studied in detail. So a number of things went into making that decision. Once the target list was selected and the telescope was launched and started collecting data, I think the biggest issue that we faced at the beginning was just how much data there were and how many planets there were. Because leading up to the mission, we didn't know necessarily how many to expect, but it was hundreds of targets within the first 2 weeks. The way that it was anticipated that we would operate as a science team, I think, had to change based upon the number of targets that came down. How do you analyze all the data? I mean, there were tens of thousands of threshold crossing events. So these are events where it looks like there's something changing in the brightness of a given star. And you had to have someone look at those individually, one at a time, going through, seeing, does this look like a planet? Does it look like a cosmic ray? Does it look like something else? And filtering out all that stuff. Eventually, all that was automated, but there was just so much stuff to do that it really, I think, caught the science team off guard with, wow, there's hundreds of, tens of thousands of things we need to look at, hundreds of systems that need to be followed up with. For example, so I was in the multi-body working group where we were looking for planets, basically looking at the dynamics of the planets in the systems. How do their orbital periods relate to each other? How many planets are in the systems? And so us being able to tell the people working on ground-based observations, these are the systems that you should prioritize over these other ones so that we could be most effective in bringing out interesting science. Because, I mean, I guess you could start just numerically, like we found this one first, so we're going to look at it first. But that eventually you might get to the end of the list. But to be honest, a lot of the targets that are on the list now still haven't been studied in great detail. I mean, there's thousands of planets to look at. And there's not that many people looking at it.
Yeah, that's fascinating that, especially in a time where all of this wasn't automated, having to go through thousands of stars just by hand. Truly, Kepler and the ones who contributed were definitely pioneering efforts when it came to understanding our universe and its origins. So what role do you think that Kepler is going to play in future efforts and missions to explore what you call these strange new worlds?
One of the main contributions that Kepler made was it showed just how many planetary systems there are and the variety of planetary systems that there are. So not all planetary systems look like the solar system, with the gas giants behaving the way that they're supposed to out in the outer parts of the system and the terrestrial planets behaving the way that they're supposed to in the inner parts of the planetary systems. There had been hints that there would be a lot of these sub-Neptunes and super-Earths on short orbits, but those hints were already just a few months before Kepler launched, was when it was known that a substantial fraction of stars would have planets that are roughly Neptune size on, a few month orbits. The mission where that result was presented was like in May, less than a year before the Kepler launch. And so Kepler was already built. And then it was like, oh, you're going to see things, and you're going to see some of these things that we've been finding in the Doppler shift surveys. Following up with that, one of the things that allowed scientists to do is once Kepler flew, we knew that there would be a lot of these small planets on close-in orbits. And therefore, you could make a survey that would allow the detection of nearby exoplanets. So because Kepler focused, its primary mission was to look for Earth-like planets in one-year orbits, which meant that it had to stare at the same patch of the sky for several years in a row in order to measure multiple transits of something like the Earth. What that meant is that it had to look, because it had to look in one part of the sky, most of the targets were far away, which meant that most of the targets were really dim. And dim targets are hard to follow up with, with a ground-based telescope. And so it takes the largest pieces of glass, it takes the most expensive instruments to get a few data points on each of these targets. But that was, in part because we didn't know that there would be so many planets on short orbits. So once Kepler flew, now you can say, oh, there's going to be, if we were to do an all-sky survey and only look for a few months in each portion of the sky, because you can't survey the entire sky all at once. You have to systematically walk your way through it. So you could build an all-sky survey and observe each patch of the sky for only a couple of months, and you would still find things. And that wasn't known before Kepler launched. So when you do an all-sky survey, now your best targets are really close to you. For example, taking an hour on some $10 million spectrograph, you can get the same information in a handful of minutes, like 5 minutes per observation instead of an hour per observation. So now you've got 20 times the number of data points that you can work with in your characterization of the different systems that you find.
Is there anything that you want to add in regards to your book or anything new about exoplanets we should be keeping an eye out for?
There's nothing that's been designed that competes with what the Kepler mission was able to provide. What's happening now in exoplanet science is that we're turning our attention towards understanding what the properties of the individual stars are, what they're made out of, what their atmospheres are made out of, what the conditions might be on their surface, efforts to find planets in younger systems, because now that we've seen results from the Kepler data, we know what systems look like when they're kind of middle-aged, and we have some idea of what their history may have been in terms of how the planets may have slightly moved around, because we see that in the solar system. We know that the planets have moved around a little bit in the solar system. After the solar system formed, the giant planets spread apart from each other over time. And so we can see similar effects in these exoplanetary systems. But now being able to focus on younger planetary systems before that evolution has taken place will also be, kind of an interesting way of understanding how our own solar system fits into the whole landscape of exoplanetary systems in general. A few of the things I think that are interesting is basically giving the reader some insight into how these missions operate. The missions are staffed with real people. They have differences in opinion. How these different people work together, the kinds of challenges that they face, how those challenges either do or don't manifest themselves out in the general public. For example, one of the things that happened with the delay in the launch and some of the changes that needed to be put in place. If you're going to build software, you have to use people to do it. And so if you're going to change the flight software, then those people who are changing the flight software aren't going to be building the data analysis software. And so one of the things that happened with the first data release is that we decided as a science team to withhold some of the data. The concern was that people might see spurious signals in the data, claim to have discovered an Earth-like planet, and then when that was later retracted, if you have a discovery of an Earth-like planet and then it gets retracted, and all that the general public hears is Kepler, then it would look bad on NASA to be like, oh yeah, we found stuff and then we unfound stuff and then we found it again. So there were all sorts of conspiracy theorists that came out of the woodworks saying that NASA was hiding stuff from the public that was, some kind of threat. 6 months later, all the data were public, including those 400 targets that we withheld. Like that kind of story and the decision-making process that goes into some of those things, it's an insight that I think is kind of interesting, basically having lived through it.
Well, definitely. Thank you for sharing your unique experience, firsthand experience. And Jason, thank you so much for joining us.
That was my pleasure.
That was Arborearian intern Jenna Weiss speaking with Jason Steffen, Associate Professor of Physics at the University of Nevada, Las Vegas, and the author of Hidden in the Heavens, How the Kepler mission's quest for new planets changed how we view our own. Still to come, the excitement of finding new worlds.
I grew up watching Star Wars and Star Trek, and so I would love to discover planets with life on them. And, intelligent life even better, but even microbial life would be incredibly fascinating.
That's ahead on Are We There Yet? You're listening to Are We There Yet? I'm Brendan Byrne. In our own solar system, NASA and partners are teaming up to search for signs of life on Mars and even on Jupiter's icy moon Europa. But aside from our own solar system, exoplanets could harbor life billions of miles away. Although the Kepler telescope is retired, there are other ways scientists and astronomers can pinpoint the location of planets orbiting other stars and possibly their atmospheric makeup. Here to talk more about how exoplanets are found and the excitement behind their discovery is Eric Perlman, a professor of physics and space sciences at Florida Tech. Eric, welcome back to the show.
Thank you.
Take us back. Exoplanets are a relatively new field of study because we just recently confirmed that they actually existed. But have scientists always thought that planets existed around the stars other than our own?
It has been something that scientists have been wondering about, basically, I think, since it was discovered that the other stars were suns. More directly, yes, scientists have always thought that most stars should have planetary systems. It's not just in Star Trek or in Star Wars. It would have been a huge mystery if our planetary system was very rare, because the process that forms planets around stars is the same process that forms the stars themselves. They form from the same nebula that the stars form from as part of the process that the stars form during. And basically, most of the properties of a planetary system writ large have something to do with the way that the sun in that particular system or suns formed.
I'm thinking back to before the heliocentric model, when we thought we were the center of the universe. It wouldn't be lost upon us to think that some people may have thought that we were the most unique because we were the only star that had planets around it, right?
I think that was a point of view that was in vogue, and there was still a debate about it even after it was known that the solar system was heliocentric. That was one of the reasons, of course, why it was a goal of astronomers as far back as the late 1800s to discover planets around other stars. There was a history of doing those things and having the attempts to do that turn out to not quite be successful, and or a claim made and then it turns out to not quite be correct. There are several attempts going back in history through the 1900s, several times where a claim was made about a planet in one or more other star systems. This was made for Epsilon Eridani. It was made for Barnard Star. It was made for some others, and they were proven incorrect until the 1990s. And what changed in the 1990s were two things. First of all, there was the discovery of a planet around a pulsar, and then there was the discovery of hot Jupiters in 1995, which is really when the field got going, because after that it was an avalanche.
Let's talk about that first discovery, a planet around a pulsar. How was that observation made, and how was it confirmed that that was indeed an exoplanet?
Pulsars are the remnants of supernovae. They are neutron stars, which are incredibly dense stars that are the mass of the sun, but only about 10 kilometers or so in diameter. So incredibly dense. The observation was made by looking at the arrival time of the pulses. If there's nothing around a pulsar, then the pulses from a pulsar are the most perfect clock that we know of in the universe. They're better than an atomic clock, actually. If there is a massive object around a pulsar, however, what it can do is it can tug the pulsar this way and that. The pulsar and the planet will both be orbiting a common center of mass, exactly the same as what's going on with our planets in our solar system and the sun, or the exoplanets in, say, any one of the objects that were discovered immediately thereafter. The only thing that was different is that this was done using the pulses. Basically, if a planet is tugging on a pulsar, what's going to happen is that it's going to be further away sometimes and a little bit closer sometimes. And so light travel time, if it's a little further away, then the pulse will be delayed.
Let me ask you this, Eric, and this may be a chicken or the egg question here, but was this discovery made by saying, hey, this pulsar's timing is off, what is doing that? Or was it, if we're going to find an exoplanet, let's look for a pulsar that has its timing off?
It was made because the pulsar's timing was off. So first of all, there's a whole bunch of people that study pulsars, of course. One of the reasons that people look at the pulses is because it tells you something about not only the spin of the pulsar, but also there are glitches in the rotation of pulsars. Basically, what that equates to is that it's a slowdown usually in the rotation rate, but we believe that it also precipitates some kind of massive quake on the surface of the pulsar or some other disturbance. It's not really clear. So they were doing this with this one pulsar, not at all having any idea that there was something going on. And in fact, one of the other reasons you use pulsars in radio astronomy is because you actually want to test how good your clock is, your timing, because they're so good. So they were doing this, right? They were looking at the pulses from this particular pulsar, and they noticed that something wasn't quite right. And then they decided to plot it. And when they plotted it, they found that it had a regular pattern to it. The solution to that pattern was that there was a planet.
I love scientific inquiry. It's like, hey, why is this timing not working? Oh, it's a planet.
Right. Well, and by the way, I mean, it's a different reason than, the kinds of things that Kepler was doing, but it amounts to a lot of the same thing. It's just a different use of variability.
So that variability that like Kepler you're talking about, that's kind of the transiting method.
That turns up as regular dimming of the object.
Right. So, okay. So you're looking at these interactions between a stellar object and you're seeing what the interaction is. And then from there, you can say, hey, there is a planet. It must be this mass, this size around it. Absolutely fascinating how you do that. So since the 90s, scientists have confirmed thousands of them. As you mentioned, this field of study has just exploded. I'm going to put you on the spot, Eric. Of those some 5,600 confirmed exoplanets, which one's your favorite?
So I happen to really love the TRAPPIST-1 system. I think it is a fascinating system. I think that what's fascinating about them, it's a whole system. It's basically a mini version of our planetary system, right? There are multiple planets that might be habitable. And the other thing that makes it really fascinating is just how much smaller the scales are. When people started looking for these things, they started looking for these things on the same scale as our planetary system. Well, TRAPPIST-1 is a much smaller star than our sun, and all of these planets fit within a radius that is roughly about a tenth of the Earth's distance from the sun. All of them, all seven. And that's just fascinating.
Yeah, I'm looking at the NASA headline when this came out. It's the largest batch of Earth-sized habitable zone planets.
And the other thing too is that with each of these, we're just at the beginning of finding out about them. What are the atmospheres like? And what temperatures are they at, and what gases are in them? We don't know these things. Is there water, volcanoes, etc.? We don't know any of these things.
How will we know that, though? There are ways to survey that, is there not?
That's right. We can find that out in a variety of ways. So first of all, JWST is doing some of that right now. When I was talking with you a couple weeks ago, I pointed out the spectroscopy of one of these transiting planet systems where the spectrum showed all kinds of interesting things, including water, as well as various other things in the atmosphere. Surface water can actually show up through polarization, because if there is scattering off of water, that actually polarizes light. And it polarizes light in a particular way that's a little bit different than, say, particulate matter, which also polarizes light. There are ways that we can find out if there is likely water, or for that matter, oxygen, carbon, whatever else, in the atmosphere or on the surface, even without going there. Nothing will, of course, substitute for going there, but that's a much more difficult thing, right? I mean, if we're going to send a probe to a planetary system 20 light years away, that's a multi-generational thing, at least with what we know now. And it's an enormously difficult endeavor.
I want to ask, what's next for exoplanets? Is the next big thing getting a direct image of one of these planets? Is that even possible?
It is possible. There are a handful of cases where a direct image has been obtained.
Oh, we've already done it.
Well, we've done it, but in each of those cases, the planet is not yet anything more than just a point of light. We know that it is an exoplanet, though. What we do is that we make one observation, and then we go back and we make additional observations. When this is done, usually there are several observations that are made, and you can see the planet moving around the star.
And what are you most excited for in the future of exoplanet studies, Eric?
I want to find worlds with life. It is not what I've made my career out of. You know that I do other things for my research, although I've gotten involved in habitability. But it's actually one of the things that fascinates me most, because I grew up watching Star Wars and Star Trek. And so I would love to discover planets with life on them. And, intelligent life even better, but even microbial life would be incredibly fascinating. I think that's far in the future, but I don't think it's that far in the future that we might discover organic compounds in the atmospheres. And I don't just mean simple organic compounds like methane and ethane, which is already being done. I mean complex things. And then I also don't think it's far in the future that we are going to be exploring the subsurface oceans on Europa, surface of Titan. These are places in our solar system that might have life.
Fascinating stuff, and I'm glad we have people like you to guide us through it. Eric Perlman, thank you so much for joining us.
Thank you, Brendan.
That was Eric Perlman, a professor of physics and space sciences at Florida Tech. That's going to do it for this week's show. If you're not already, be sure to subscribe to the show's podcast feed so you never miss an episode. Do that on the NPR One app, Apple Podcasts, Spotify, YouTube, or really wherever you get your podcasts. Stay connected with this show. Be sure to follow us on social media. You can find us on Instagram and Facebook, and now Blue Sky. And if you got an idea for a future episode of this show, or you want to join us as a guest, reach out. Give us an email. We're at arewethereyet@cfpublic.org. More space coverage is online. Visit cfpublic.org/space. Are We There Yet is a production of Central Florida Public Media. Our producer is Marion Summerall. Our intern is Jenna Weiss. Editorial guidance from Latoya Dennis. Support for Are We There Yet comes from our listeners. Until next week, I'm Brendan Byrne. Thanks for listening.